Good morning. My name is Vanshika from BSc Chemistry Honors Final Year. In this audio lecture for visually impaired student, I have taken the topic hard and soft acids and bases from the book Inorganic Chemistry, Pradeep's publication by Dr. K. Bhasin. So let's start with hard and soft acid and bases. The terms acids and bases are routinely used in our daily life. Chemists have been classifying substances as acids and bases since long time. Lavoisier noted that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius developed the theory of acids and bases, known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions, that is H positive, in aqueous solution, and a base is a substance which gives hydroxyl ions, that is OH negative, in aqueous solution. The strength of an acid or a base depend upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative converted to H2O. In 1923, J. N. Bronsted in Denmark and T. M. Lowry in Great Britain independently proposed a new acid-base theory. According to this theory, an acid is a proton donor whereas a base is a proton acceptor. The acid-base reaction, that is the neutralization, is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definition of acids and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turns red litmus blue. However, tasting and feeling chemicals are dangerous methods of determining whether the substance is an acid or a base. You should never ever taste or touch solutions of chemicals in laboratory. There are, however, other methods of recognizing acids and bases. For example, acids and bases change the color of certain dyes known popularly as indicators. One of the most common indicator is a vegetable dye obtained from lichen known as litmus. Aqueous solution of acids turns the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electrons can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances capable of accepting a pair of electrons are regarded as Lewis acids. Acid base or neutralization reaction may thus be regarded as donor acceptor reactions or coordinate covalent bond formation reactions. The classical example of Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is the Lewis base. So Lewis base NH3 plus Lewis acid BF3, it is converted into NH3BF3 donor receptor or coordinate bond formation reaction. Lewis concept of acids and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compounds can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ions can be regarded as Lewis acids. The degree of affinity of a metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. So hard and soft acids and bases. An acid-base reaction, according to Lewis' concept, involves the reaction between a donor and an acceptor as to form a complex as given below. A plus B form AB complex. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive and Pt4 positive. Based upon the preferential bonding, the acids and bases have been classified into two groups, class A and class B, according to their preference. So class A metal ions includes alkali metals, alkaline earth metals, lighter and more highly charged ions. For example, chromium 3 positive, aluminium 3 positive, tin 4 positive, iron 3 positive, cobalt 3 positive, etc. and hydrogen ion H positive. Class B metal ions includes heavier transition metals of second and third transition series, that is cadmium 2 positive, mercury 2 positive, palladium 2 positive, platinum 2 positive. Second, heavier transition metals in lower oxidation state, Ag positive, Cu positive, Hg2 2 positive. Low valent metal ions such as zero valent metals in metal carbonyls. Depending upon the type of metal ions, ligands can also be classified as class A or class B depending upon their preference. Class A ligands include molecules or ions with donor atoms NO, F, Cl, etc. It is important to note that class A ligands prefer to form strong complexes with class A metals. Class B ligands includes molecules, ions with donor atoms, phosphorus, arsenic, selenium, iodine, etc. Class B ligands prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acid and bases for class A and class B metal ions and ligands. Accordingly, class A metal ions are referred to hard acids, while class B metal ions are called soft acids. Similarly, class A ligands are named as hard bases, whereas class B ligands are termed as soft bases. In summary, according to Pearson, class A acids are hard acids including H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive, etc. Class B acids are soft acids including Ag positive, Pd2 positive, Cu positive, Pt2 positive, etc. Class A bases are hard bases including H2O, NH3, F negative, ROH, etc. Class B bases are soft bases including R3P, R3AS, R2S, R2SE, I negative, SCN negative, etc. Classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid base interaction on the basis of hard and soft acids and bases. He observed that type A metal ions, that is acids, were small, compact and not very polarizable, and these preferred ligands, that is bases, that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed that hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. A general classification of some common hard and soft acids along with some borderline cases is given. For example, hard acids are H positive, Li positive, Na positive, K positive, etc. Soft acids Cu2 positive, Ag positive, Au positive, etc. Borderline acids Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive and Zn2 positive, etc. So it reveals that hard acid usually have the following characteristics. First, hard acids are cations of smaller size or lighter elements. Second, hard acids are cations of higher oxidation state. For example, Cl3 positive, Cl7 positive, I5 positive and I7 positive. Hard acids are molecules cations with lesser number of valence electrons. Hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small sized, compact and are not easily polarizable. On the other hand, soft acids possess the following characteristics. Soft acids are cations of the large size or heavier elements. Soft acids are the cations of lower charge. Soft acids are the molecules ions with large number of valence electrons. Soft acids do not hold the valence electrons tightly and are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ions molecules that bind strongly to highly polarizable ion molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard nor soft are called borderline acids, which are shown in the table in some examples above. Borderline acids have properties which are intermediate between that of the hard acid and a hard base. In case of borderline acids, the properties such as size, oxidation state, polarizability of the cation are neither too low nor too high. On the other hand, soft acids will show the opposite trend and following order of preference for binding the donor atoms ions within the group is observed. Order is first of all I negative, then Br negative, then Cl negative, F negative, R2Te, R2Sc, R2S, R2O, then R3Sb greater than R3As is greater than R3P is greater than R3N. Now classification of bases. A general classification of some commonly used ligands, that is Lewis bases, into hard and soft bases along with the borderline bases is presented in the table. Like hard bases are F negative, Cl negative, NH3, RNH2, N2H4, ROH, H2O, R2O, OH negative, NO3 negative, etc., where R is an alkyl group. Soft bases are H negative, R negative, I negative, C2H4, C6H6, RSH, R2S, RS negative, Cn negative, SCN negative, S2O32 negative, R3P, R3AS. Borderline bases are Br negative, C5H5N, C6H5NH2, N2, N3 negative, NO2 negative, SO32 negative, CORNC. So hard bases bind strongly to the proton. Hard bases contain donor atoms of high electronegativity. The donor atoms in hard bases possess low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. It reveals that the following features are observed in case of soft bases also. Soft bases contain donor atoms of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative non-metals including carbon, sulfur, phosphorus and iodine. The donor atoms in such bases possess donor atoms that are easily polarizable. Just as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of soft and hard bases. So, this is all about hard acids and hard bases. Thank you.